All right, so this is the first of 3 review lessons on factoring, although by the end of it, it may not feel like review. And for a lot of these, we may go a little bit beyond what you may be used to from Math 10, but it's all concepts, definitely building upon concepts I'm hoping you're familiar with or were familiar with at one point. Anytime we have to factor, and keep in mind factoring is unmultiplying. Unmultiplying is not a word. Factoring is. But, factoring really goes back to elementary school. For example, if you want to factor 12, you think what multiplies into 12? Well, for example, 6 times 2 multiplies into 12. So 6 and 2 are factors of 12. However, in this case, 6 can be broken up even more. And 6 is the same as 3 times 2 times 2. So we say this is fully factored. And that's factoring in elementary school. The factors of 12 are 3 times 2 times 2. Well, factoring a polynomial is similar, although again we have variables. And the first thing you always want to check for if you're trying to factor something is there a GCF? Is there a greatest common factor? If there is, pull it out right away. And so if I look at this first expression right here, 8a cubed minus 12a squared plus a, is there something I can divide out of everything nicely? And yes, there's an a. There's a factor of a I can divide out of everything. So a is the greatest common factor. So I'm going to take a factor of a out of everything. So when I pull a factor of a out, it's really no different than when I had 12 and I said the same as 6 times 2. 6 is a factor. And so how do I get the 2? Well, essentially, you're going 12 divided by 6, or thinking 6 times what equals 12. So in this case, when I take out that factor of a, what remains here? Well, essentially, I'm dividing all these things by a. Or what times a equals all this stuff above. So in the end, and again, this should be something that you've learned about before, but this first term will be 8a squared. Because 8a cubed divided by a is 8a squared. Or if you go backwards, a times 8a squared is 8a cubed. And so similarly, the second term will be minus 12 just a plus 1. A common mistake is I think this is a 0, but again, a divided by itself is 1. Anything divided by itself is 1, not 0. There we go. Done. All right. Now, one thing we should always do next is see, can we factor this further? Now, this is the first factoring lesson, so we can't. But you should always, once you've taken a GCF, don't assume there's not more you can do. Just like, again, going back to my example of 12. 12 is the same as 6 times 2, but 6 can be broken up even more. All right, let's look at this one here. Again, look for a GCF. What's the largest, not just a common factor, I want the greatest common factor. And the greatest common factor, the largest expression I can take out of everything here nicely is a squared and b, a squared b. Everything here can be divided by a squared b. And so when I do that, what's left? I have a, because again, if it helps, show that it's being divided by a squared b. The b's cancel out. A cubed divided by a squared is just a. But again, if we write this down every time, it's not a bad idea. Just kind of slow and maybe adds extra steps and can get kind of tedious writing this out every time. But again, at the early stages, this can be a very good idea to remind you why I'm getting these terms. This next term is going to be minus 5a because the a squareds completely cancel out. And the last term is going to be plus 10b squared. Again, the a's completely cancel it out. In this case, one of the b's canceled out with one of these. But not to make too much of a mess of all my work, there was the original expression. Here's my factored expression. Okay, with that said, when most students think of factoring, they don't actually think of this right away. They think of this, factoring a trinomial like this. And in general, if you have a trinomial, 3 terms, where you have a coefficient of 1 in front of the x squared, and you have 3 terms, it can usually be really, really quick to factor these. And if this can be factored, it's always going to be a matter of thinking about, well, what 2 numbers go here and here? And again, this should be review. But in the end, whatever those 2 numbers are, they must be integers, which means they may be negative, but they're going to be whole values. And we've got to think to ourselves, what are 2 integers that multiply to c, whatever that last constant is? So you got to think what 2 numbers multiply to c. Now there's whatever the number, there's always going to be lots of options. But at the same time, we also want to think about 2 integers. Again, they will be whole values, but they may be negative, that add to b. And if you look at that in isolation, there's too many options, but put the two together. Think about both these comments. What are two numbers, two integers that multiply to c and add to the middle coefficient? Then, if it can be factored, there's only one pair of correct answers. And whatever those two integers are, that's what goes here and here. And keep in mind, they may be negative. And if it's a negative number, you're adding a negative, so it's like you're subtracting. But again, I say this quickly because, well, you've learned this before, so now it's a matter of just reviewing it. So I'm going to do a whole bunch of quick little examples here. And so for this first one, I need to think of two numbers that multiply to 27, positive 27, yet add to 12. Again, there's countless options that multiply to 27. But if we think about integers, there's still a lot. And there's literally countless options that add to 12 when you think about negatives. But put the two together, there's only one possibility. And the only pair of numbers that work, the only two numbers that multiply to 27 and add to 12 are positive 3 and positive 9. So those are my two factors. Positive 3 and positive 9 multiply to 27. Positive 3 plus positive 9 is positive 12. Nothing else works. Oh, so for this one, similarly, we have has to add to 6 and multiply to negative 27. That gives us a sign there's going to be at least one negative number. In this case, it's actually going to be, just one. And so we have negative 3 and positive 9 are the only two numbers that multiply to negative 27 and add to 6. Now, all of this feels really easy if you have a good, confident memory of your multiplication tables. And you're quite confident with adding and subtracting integers in your head. If those things aren't down so much, then this seems much more difficult. It really is all based on a lot of our basic math facts from earlier grades. Lastly, if this can be factored, if you can find two numbers that multiply to negative 27, you'd add to negative 6. And the only way it's going to work is if you have negative 9 and positive 3. Again, only negative 9 and positive 3 multiply to negative 27 and add to negative 6. By far the most common mistake is having the wrong sign. For example, maybe having these answers mixed up from one another. Having the right idea, but having your signs wrong. By far the most common mistake. But we should never actually have to make a mistake if we just take a moment to check. When I said check, just like I've been doing, like just check. Do these two numbers indeed multiply to this and add to this? If they do, you're right. There's no, otherwise you're wrong. Like there's no in between. All right, let's look at a few more examples, getting a little bit different looking. Okay, the one on the left is the most straightforward. What multiplies to 20 but adds to negative 12? What two numbers? The only two numbers that work are negative 2 and negative 10. Those are my factors. The next one, notice, is very similar. I have that negative 12, I have the positive 20, but there's this extra y variable building up. Well, again, when we're factoring, we're unmultiplying, which means we can always, if we go backwards, for example, if I look at this first one, if I FOIL this out, 1, 2, 3, 4, I should collect like terms and get this. So for this next one, it's extremely similar to the first question, but yeah, there are these extra y's here. Well, one thing you could do is just ignore them for a moment, pretend they weren't there. And if those y's weren't there, this would be the exact same as the previous question, which means I know the factors. If the y wasn't there, the factors must be x minus 2 and x minus 10. So if there were no y variables, it would be the exact same as before. But there are these y variables. So what difference does it make? Well, just they're going to be here. And again, if you're not sure why, no pun intended, by the way, then just double check, go back, multiply. X times x is x squared. X times minus 10y is minus 10xy. We're starting to get a mix of x and y together. Negative 2y times x is negative 2xy. And notice when I combine these like terms together, I get negative 12xy. And my very last step, negative 2y times negative 10y is positive 20y squared. So in the end, as long as we're not too thrown off by how it looks a little bit different, it's pretty much identical to the idea from before. And as long as we are proficient with distributing binomials like this, foiling it out, then it makes sense how this would work. Last one looks kind of weird too. We have a power of 4. But again, the same structure as all these previous ones. And so for this, again, the factors of this are going to be the same as before. Minus 2 and minus 10. But this time it's going to be x squared. And again, how do I know that? Because again, the very first thing I would do is go x squared times x squared is x to the power of 4. And if you do the same next steps and FOIL it all out, it will all come back to this. So keep in mind, again, all three of these were different, but they were all closely related. The one on the left was the most straightforward. The ones in the middle and the right were a little more unfamiliar, but they're all set up in the same sort of way. And this is why I say some of these things may be kind of new. You probably did not do this in Math 10. Maybe, but it's supplementary. Okay, but it's just building upon those things. So similarly here, different looking examples that are all related. The one on the left is the most straightforward. What multiplies a negative 56 but adds to positive 1. Again, if you don't see a coefficient, you can always put a 1 in. And the only two numbers that work are negative 7 and positive 8. So those are your two factors, x minus 7, x plus 8. And that relates similarly to all the other ones. Just recording something right now. You can give me 2 minutes? Okay, yeah. And so for this right here, if I take a factor of 2 out first, because again, you should always look for a greatest common factor, then I suddenly have x squared plus x minus 56 left. And now once I do that, once I thought about looking for a GCF, which again we should always look for, well, lo and behold, what you see right here is identical to what we have right here, which means it must be identical to what we have right here. So I can just now realize there must be 3 factors here. Right, and so lastly, similar idea. You may get thrown off by this power of 3 and whatnot, but again, we should always look for a GCF, and in this case, the GCF is x. And so if we take out a factor of x right here, thank you very much.
There's a treat out there for you, and I know you want one.
Oh, okay.
Regarding ice cream, give him a break for a second.
Thank you. Hold that thought. Sorry, I'm getting a very important delivery right here. Thank you very much. Thank you very much. And so as I take out that factor of x, which again is the greatest common factor of these 3 terms, I'm left with just x squared plus x minus 56. And then again, you've noticed how uncreative I've been. Everything you see here highlighted in yellow is equivalent. So I don't need to reinvent the wheel. I could just copy my previous work. And so again, these are the fully factored final answers. And so in this case again, if we didn't think of looking for a GCF on these, we're either going to make it much harder on ourselves or more likely we'll just get stuck. Always look for a GCF at first. And so for this final problem, I'm just going to leave it here. This is something I'd rather talk about in class. So I guess that means I'm done.